Okay, so I hope I'm audible. Uh, yeah, let me check. Okay, so yeah, we'll start with the sessions on week four, wheel mobile robots. So I hope the courses have been going well for you. So until now, we have been discussing the mechanics of wheel mobile robots. So far, we have actually covered for week one, we basically have covered the topics such as kinematics for weeks one and two. And for week three, we have also covered dynamics of wheel mobile robots. So we have discussed in detail how to dynamically model the wheel mobile robots using two different methodologies. One we have discussed is what we call as this Euler-Lagrange method, and the second being a momentum-based Newton-Euler method. So yeah, so for that we'll actually take a new step from week four onwards. So weeks four, five, and six mostly deal with the topics such as sensors and perception. So that is what we cover on week four. That is today's session. And for next week, we'll cover localization and navigation. And for week six, we will cover path planning algorithms. So yeah, just like how we did for the last 3 weeks, we'll begin with a summary of all the important key topics that we have uh, discussed in the lectures, taken by the professor. And for the remaining part of the session, we'll solve some sample tutorial questions that may help you to solve the weekly quizzes. Okay, so until now, with whatever we have covered so far, the topics that is mostly mechanics of wheel mobile robots, we will be able to control a mobile robot using teleoperation. Like it, until now, we haven't discussed or we haven't introduced any concepts of autonomy of mobile robots. But whatever we have discussed is more or less essential to control it using a joystick. Maybe since we know the kinematics and dynamics, uh, if we can map our desired trajectory to the specific configuration of wheel mobile robot that we are interested in, we can easily control it using a joystick or even using a simple controller. But that is not basically this end of the application that a mobile robot can be deployed in. So a lot of applications we require autonomy actually. Like we want the mobile robot uh, to make its own decision and to move on its own without any external interferences. So such processes require some level of autonomy, and as a consequence, it may require some sort of capabilities in sensing, perception, and navigation. So yeah, so we'll basically discuss a few key aspects regarding perception, because like if you can recall what we have discussed in the week one lectures, we we know that a mobile robot basically works on an unconstrained environment rather than a robot manipulator, because a robot manipulator, the base of a robot manipulator is always fixed. So its work area is basically fully constrained. So we would know how a fixed base manipulator would move exactly on a spatial coordinate system. Whereas in case of a mobile robot, it is fully unconstrained. It has no constraints on it. It can move anywhere on its environment. So in order for us to facilitate a safe movement of a mobile robot, it requires sensors to perceive what is going around on this environment. So yeah, we'll discuss regarding that. So this week, as I've said earlier, it is mostly about sensing and perception. So this week is mostly about the sensors actually, and how we can use the sensors to perceive what is going on around around this environment. And what basically the first slide I would like to share with you, you might have seen in the lectures, is basically a graph that correlates the complexity of a task and the level of autonomy. So if you see this axis, if you consider this axis, it basically shows the level of autonomy. So starting from teleoperation, it it has zero level of autonomy for a teleoperation application. And if you go all the way along this axis, you will end up with a fully autonomous mobile robot. Whereas if you take a look at this axis, it basically depicts the increasing level of the task complexity. And as you can see, where we would mostly deploy a remote operation or a mobile robot that is fully supervised by an external operator for a task that is highly complex, right? But as the complexity of the task decreases, we may find it more and more easier or more and more convenient to uh, introduce some level of autonomy for a mobile robot. So, like if you can see, if you take a look at this uh, region where we deploy autonomous robots, the task complexity is comparatively very low. But the level of autonomy we have for such kind of robots is actually very high. And in between, you have something called a hybrid mode of operation where it can have some level of autonomy, and when the tasks get more complicated, an operator can actually interfere, or an operator can actually take over some of the autonomous operation so that it can be more supervised actually. Yes, the thing is that like we still haven't reached a full level of maturity regarding sensors and actuators, because as you would see in the later on this lecture, sensors have some sort of errors inbuilt, errors that we cannot fully model. So due to that fact, we cannot fully deploy on tasks that is fully complex, in the sense like, we cannot exactly deploy a fully autonomous robot that can replicate what a human being is actually doing. The complicated jobs a human being can do. We cannot deploy an autonomous robot because we haven't reached that level of maturity in terms of actuators and sensors. So yeah, that is where autonomous robots comes into picture. Maybe for smaller, more repeatable tasks, but with less complexity, we can actually use an autonomous robot. So like on the long term, it could be much more cost effective rather than employing uh, human being actually. Right. So moving on, we will basically uh, discuss the key differences between teleoperation and autonomous modes of operation. So just like what we have seen in the previous lecture. So telerobotics over here on to your right hand side is basically the area of robotics which deals with the control of semi-autonomous robots from a distance, mainly through wireless connections or tethered connections. So just like how, like if you build a robot, a mobile robot, and if you can basically control the motion of a mobile robot just by using a joystick. Maybe if you push the trigger forward, it may move forward. If you move the joystick sidewise, it may move sidewise. So the entire movement of a mobile robot would be fully controlled by a joystick. You could consider the joystick as a a master device, and the robot itself as a slave device. So all the commands are actually made by a human operator through a slave device, and the communication between a slave device and the master device could be made possible through a wireless connection such as Bluetooth, Wi-Fi, or even through tethered connections, right? And the next part basically comes as autonomous mode, where the robot is fully autonomous. The interference of an external operator is kept quite minimal. And if you take a look at this telerobotics, there are two subfields called teleoperation and telepresence. So teleoperation is basically if a robot is controlled remotely by a human operator. For example, the robot could be on a different place. Like for example, if you take a look at rovers in extraterrestrial applications, maybe a rover in Mars, it's fully controlled by operators on stationed on a mission control on Earth, actually. So whatever operation an extraterrestrial robot will have to do, it's fully controlled by an external operator, actually controlling it from a terrestrial base. And the another aspect is telepresence. Basically, it's and as per the definition, it is just to give a better sense of remote physical presence for communication and collaboration. Like for example, like these days you have these tactile robots where if you want to feel something, if you want to feel an environment, for example, uh, if a supervisor is actually not on site and if he wants to feel a finished product, or if he wants to feel something, how an object would look, or how an object would feel, just like how he would feel using his hands, he could use this tactile robot. So it can give us similar sort of feedback on how basically how an object can feel. So similar things can also be thing. So a person will does not really have to be there on site in order for us to really communicate or collaborate with whatever is being on site. So yeah, that are the two aspects. We have teleoperation and telepresence, and this is actually completely different from autonomous mode, where instead of human intervention, the robot itself will have to answer uh, these questions actually. So the most important questions an autonomous robot will have to answer are, where am I? Because the robot on its own, probably when it is being started for the first time, will not have any sense of position, or it may not even have any sense of its own location actually. So it needs to identify, if it is being provided a map, a mobile robot needs to know where it is currently deployed on a map that it has been programmed on. And where am I going to? So if a command has been given with respect to a map that has been programmed onto the robot, it needs to know where it is going based on some reference. And how do I get there? Like if it solves this problem, if it knows where it is exactly there on a map, and if it also know uh, where it should be going, it also need to know how it can reach there. Maybe it can have a lot of different criteria. One criteria could be, which of these paths would uh, would consume least amount of energy. There could be multiple solutions actually, and which would be the most efficient way of reaching a goal position. So all these things you will be going through in the later weeks actually. So in this week, we'll mostly related to sensors, perception and sensors. And more about this, you can see this on weeks 5 and 6 lectures. And all these problems can be addressed through different aspects or different sub fields of mobile robots. The first being locomotion. So we have basically seen the principles of locomotion or the mechanics of locomotions on week 1 and 2. Navigation, which deals with perception and localization. We'll basically learn the principles of perception for week 4, that is during these lectures. And localization, you would be basically covering on week 5. And the further step is planning. So planning basically deals with how it should go from its start position to the goal position. And motion control, basically motion control also deals with controlling the actuators. So once the planning has been done, the commands that a robot should be giving to these actuators. For example, if it's a mobile robot, what are the commands that should be given to the motors? All these things comes under motion control. So these are the important subfields of a wheel mobile robot. So we can see that these aspects in more detail on this slide. I hope you can recall this from the lectures from Professor Ashokan. So this is basically a never-ending cycle. It's an infinite cycle. It keeps going on. It keeps going on and on as long as the robot is moving. So if you consider the first point being the real world environment, if you consider this to be the start of this loop, so the first step is basically the perception. The first step a mobile robot will have to execute is to perceive its real world environment. What are the features that is present on this environment? Where are these obstacles? All these things it can learn through sensing, or in other words, we can call all this whatever is being contained in this block through a blanket term called perception, which consists of sensing. So sensing is basically is how using sensors, what you perceive through this environment, you can basically detect it through sensors. And whatever you have from the sensors is basically a raw data. Like the entirety of the data may not be useful. You would be looking for specific features. So you need to find a way to extract the features that we may be looking for. For example, like if the robot is actually if the robot is actually locomoting by identifying some landmarks on this environment, it needs to identify the landmarks from the image that it is capturing live, right? Because everything else, maybe all the surrounding things, you could simply consider it to be noise. Only the relevant features need to be extracted. So that is where this step comes in. From the raw data that it is getting from the sensors, it needs to extract only the relevant information through feature extraction. And in most of the cases, the robot will be basically given a map where it is operating. So we'll basically provide a robot a map of its environment. And based on that map and based on the readings from the sensors, maybe from the landmarks, the robot should be able to localize itself. So like initially the robot, if this is a map and if this is a robot, it may not even know where its position is currently. So with the map, with the map already given to the robot, the map has some key landmarks. So based on the sensors, it could basically identify its relative position from each of these landmarks. So with that, it can basically localize itself, its current position on the map. So that is where we call a localization. And there could be some features that may not be available, that was not available on the map when it was applied. Maybe there could be more features, there could be more obstacles on the map. So while localizing itself or while learning all the features of the map, it keeps on updating the map, right? So that is where this step comes in. So even though we are providing a map, it keeps on building or it keeps on updating the map based on what it is learning currently or on real time. And basically it creates a global map, a global position map uh, where it basically updates what it learns, and it also updates its current position, as well as simultaneously it also creates a map uh, incorporating all the new features. And yes, once it has done that, the next step would be cognition. So basically, it needs to know where it should be going. So a mobile robot will have a target, a goal position. So maybe if it starts from a position, it may have to do some purpose at its final position. Maybe if you call this as a start position, and at the end you have a goal position. So a robot will need to traverse from a start position to goal position in order for it to do some task. So how do it get there? So how to get there? So that is what it basically do in this step. It creates a path. It creates the most ideal path from the start position to the goal position, avoiding all the obstacles and maybe taking the route that consumes the least amount of energy. And from here, it basically, once the path has been planned, it basically gives its commands to the actuators using a motion controller. Like even if the path has been created, if it identifies a path along its map, it needs to ensure that the robot stays on the path. How does it do that? It does that by the motion control subsystem of a robot basically ensures that the robot stays on the path. So it may take feedbacks from its own internal encoders. It may also take readings from its sensors. So it by comparing all the data internally from the robot as well as what it is receiving externally, it will make sure that the robot will stay on the path that was already planned or already selected during the path planning process. So the controller basically makes sure that the robot stays on the path without veering too much from the desired path, and it also gives the commands to the actuators. So these are basically actuators, and it is the actuators that are essentially driving a mobile robot. So the motion controller ensures that the robot stays on the path while giving the necessary input commands to the actuators. And further, it updates its new position and it keeps on going, on an infinite loop as long as the robot is still in operation. So, like I've said, what we are discussing for this week is perception. So, the key definition of a perception on a broader term is nothing but that is the process by which people translate sensory impressions into a coherent, unified view of the world around them. So, if you take a look at whatever we are, if you take a case of a human being, we may be getting all sorts of feedback from this environment. So if you simply consider your eyes, you are basically seeing all the relevant objects that is being you know that is being sensed through the eyes. So like for example, if you are driving, you only focus on the important bits, maybe the road ahead of you, how the vehicles are moving in front of you, the traffic lights, the road signs, everything. You may choose to discard all the other distracting aspects, maybe of the poster of a movie that you see at the side of the road, or maybe the name of a shop that you may be interested. All these things you would be ignoring because your purpose is to drive a vehicle, and all the other extra set of informations you choose to ignore it. So that is exactly what a robot does, because from the raw sensor data that it is getting, it only needs to create, it only needs to capture what is actually relevant to them. Maybe if it goes by sensing some sort of landmarks or some sort of markers, it only needs to get the data, or it only needs to extract where these markers are being placed along the path. So that is also what a mobile robot does. So it basically translates some sensory impressions into a coherent, unified view of the world around them. So extracting what is relevant to a to the locomotion of a robot, it only needs to extract that so that it can basically have a coherent view of its own environment. So for the perception of a mobile robot, these are the steps, or these are the processes that uh, you could use these processes to more or less define how a mobile robot perceives, or how to quantify how what a mobile robot perceives. So these are sensors. It could be any sensors. Maybe it could be vision sensors, proximity sensors, distance sensors. So from the raw data of the sensors, it extracts only the relevant features that it may require, and from here it goes to matching with uh, what it has been told to observe. So, like for example, if the robot is already asked, or if the robot is already programmed to just to look for these features at a specific point of time, or the specific instant, it compares with the features that is already provided onto the robot with what is incoming from the sensors. And if it is actually seeing what it is expected to see, or if it is seeing what it is supposed to see, it will update that it's going through the right path. Or if it is not seeing what it is supposed to see, if it is sensing something unexpected, it will again incorporate into the model, and it basically updates. It will basically take some corrective action so that it will come to this ideal path. Whatever be the case, it will integrate into this model. It will incorporate whatever it founds through the features into the model. And once it is applied to the model, so the model is basically a robotic system which has all the four subsystems like perception, localization, navigation, path planning, and control. Everything is comprised on the model. And depending on what is being taken from the sensors, it will give a new prediction. If it is a corrective measure, it will take a corrective measure. Or if it is satisfactory, if the uh, uh, performance of the mobile robot is satisfactory, it will update its next course of action, how to proceed forward. Whatever be the case, whether it is to correct its trajectory, or maybe to update its own updates its further position or position of the next instance, it will do this via this step. And again, like once it is updated, it should also it will give the next set of feature the robot is supposed to see, and it matches with what it is currently seeing, and basically it runs on a loop on a so yeah, the next step is to like since we are still on the topic of perceptions, we need to be aware of all the sensors that can be employed on a mobile robot used for its own perception. So speaking of sensors, like most of the content of this week, I think we have 3 weeks dedicated to the discussions of sensors, right? Out of all the 6 lectures on week 4. So we probably won't go through all the sensors because these are more or less theoretical, and you can actually go through the lectures by Professor Shogun in order for you to gain a better understanding of the working of each of these individual sensors. But we will cover the key points actually more, just like key points such as how various sensors can be classified. So if you can recall, there are two key ways that you can actually classify a sensor, whether it is a proprioceptive or an exteroceptive sensor. This is one way of classification, and this is another way of classification, whether the sensor is active or whether the sensor is passive. So yeah, these are basically the two different way of classifying sensors. We'll go through each of them one by one. So what proprioceptive sensors means? Proprioceptive sensors are basically sensors to measure values internally to the system. So like in values internally the system, that what it means, those are the readings that is crucial for the working of the mobile robot. Like for example, if you talk about encoders, rotary encoders, that is pretty much essential for the locomotion of a robot. So and it could be battery status sensors, sensors to monitor the status of battery. Then what else? The sensors to measure its orientation, maybe inclinometers, gyroscopes, and all those things. So everything that measures values internally to the system, those comes under proprioceptive sensors. And the second classification is called exteroceptive sensors. So which gathers information external to the robot. For example, like if you want to know how close a robot is to an object, you can measure it through proximity sensors. So those things measure parameters or environmental measures that is external to the robot. Another of such examples could be the intensity of ambient light. If you can use the sensors, like for example, our mobile phones and smartphones have, smart watches have this ambient light sensors, so that it can automatically adjust the brightness of the display depending on the level of light it is receiving. And maybe also some unique features. For example, using CCD cameras, it can basically take raw photographs or raw images of its environment. So that is one kind of classification, proprioceptive and exteroceptive. The another kind of classification is called active and passive sensors. So as the name implies, passive sensors utilizes its own energy coming from this environment. Like for example, if you might have heard about piezoelectric sensors, maybe depending on the force that it is being supplied on the piezoelectric sensor, it basically produces a charge or electric current. So by measuring that, you can have an estimate of the force that it is being subjected on a piezoelectric crystal. And you probably won't need to provide any energy for the energy to actuate or to make the sensor work. It gathers energy from outside this environment. You don't need to provide any sort of energy for the functioning of the sensors. And the second kind comes under active sensors. So for the functioning of such sensors, you need to give some sort of energy for us to activate the sensor. Like for example, what can you say? If the sensor has to emit some sort of energy, it basically measures its reaction, how it reacts with the environment, and based on the reaction, based on the measurements of the reaction, it can estimate what that sensor is basically doing. Like for example, if you know this ultrasonic sensors. So what it does is it transmits a wave or a sound wave from its transmitter, and based on the time from its transmission and its reception, if it is nearby an object, it will go, it'll fall onto an object and it will reflect back to its own receiver. You can basically use the time for it to come back, time for the sound wave to come back and be captured by the receptors as a measure of the distance, actually, right? If you have a transmitter and a receiver here, and the time for it to go forward and be reflected and come back to be captured by the receiver, you can use that as a measure of the distance for this ultrasonic sensors. And in order for it to do that, it has to emit some energy, right? It has to emit some sound waves. So that is what we meant by active sensors, because you have to give some sort of an energy onto those sensors for the functioning of those sensors. So those kinds of sensors comes under active sensors, right? So I hope that is clear. The two kinds of classification of sensors: proprioceptive and exteroceptive, active and passive sensors. And on the lectures, you have basically been given a comprehensive list of sensors and how it can be classified, whether it is proprioceptive or exteroceptive on this column, or whether it is an active or a passive sensors. So, like for example, if you consider this column, you have a class of tactile sensors, and there are different kinds of tactile sensors that you can use. So the one example being the contact switches. So contact switches are bumpers. You can attach a bumper kind of a thing on external to a mobile robot, and based on how it is compressed or how much force it is being subjected to, it can basically generate some sort of an electric current, and you can measure that electric current as a measure of how much force it is being subjected on. So like since it measures an external attribute, it's an exteroceptive sensor. And due to the fact that you don't have to provide any sort of energy onto the system, it gathers energy from this external interaction. It is a passive sensor. But whereas in the case of optical barriers, those are also exteroceptive sensors. And since you have to provide some sort of energy, like it's an optical barrier, so it has to emit some sort of light energy or some sort of energy, it has to be an active sensor. And similar in the case of non-proximity sensors, for example, ultrasonic sensors. So it does not have to be in contact with any bodies. Even without contact, it can basically measure the time taken for the beam of the sound to go from its transmitter to get reflected back its own receiver. And based on the time it takes, based on the time the sound wave takes to traverse from its transmitter and to get captured by its receiver, it can basically measure the distance actually. So in that regard, that is also an exteroceptive sensor, and due to the fact that some sort of an energy have to be supplied, those also comes under active sensors. So for example, this tactile sensors are, without any doubt, you can actually see that all sort of tactile sensors, whether it is passive or active, everything comes under exteroceptive sensors. Whereas in the case of wheel motor sensors, wheel motor sensors to identify the angular velocity or angular position of the wheel, those things basically measure attributes that are internal to a system, measures values that are internal to the system. So whatever be the kind of wheel sensors that you have, since it is measuring something internal to the robotic system, each and every one of the wheel motor sensors are proprioceptive sensors, right? And depending on the kind of sensor that you are using, it could be passive sensors or an active sensor. Like for example, if you have brush encoders, brush encoders are nothing but passive encoders. But if you're using optical encoders, if you pulse a light beam through an encoder, and depending on the number of pulses the receiver is capturing on the other side, it can basically determine whether the robot, it can basically have a measure of its angular velocity. So since it has to emit some sort of a light beam, maybe a laser beam or pulsing LED, since an energy have to be emitted by it, it has to be an active sensor, right? And so the same thing goes for heading sensors. But in case of an heading sensor, it can basically be proprioceptive, exteroceptive, or proprioceptive, depending on where it is basically deployed. So if it is an inclinometer, just to see whether how the robot is actually, whether it is climbing or whether it is having any sort of rolling motion, in order for it to determine that, these sensors will have to be mounted external to this thing, and it basically measures something that is external to the robot. Maybe the Earth's magnetic field. It has to measure Earth magnetic field to get a sense of its heading. So in that regard, it could be exteroceptive sensors. For example, a compass is basically influenced by the Earth's magnetic field. So in that regard, it could be an exteroceptive sensors, right? And due to the fact that we don't have to provide any sort of energy to a compass, it also comes under a passive sensor, right? So multiple kinds of different variations of sensors are also possible. Like for example, you can have various kinds of inclinometers. Inclinometers that could be active and that could be passive, right? And same thing for ground-based beacons. In order for it to localize a robot based on a given map, you could use GPS. You could use beacons. Maybe how a ship navigates using buoys deployed on water bodies. It may have some sort of tracking devices or receivers. So using that, it can also, whatever that we are interested in tracking, you can also identify their position. So yeah, most of those things comes under exteroceptive sensors because it also measures something that is external to a robot. And due to the fact that it also involves some sort of energy, those are all active sensors. For example, GPSs, it emits radio waves, or it emits radio waves that has to be received by a receiver. So in that regard, most of the cases of ground-based beacons, they are all active sensors. Yeah, and similar thing, like maybe motion speed sensors, to have a measure of uh, speed or motion of a moving object, you can use this Doppler principle, to measure the relative change of frequency as a measure of how fast an object is moving away from a receiver or away from towards a receiver. So you can use the Doppler effect as a measure of the relative speed between a transmitting and a receiving objects. So in that regard, also most of those things, relying on the principles of Doppler effect, those also mostly comes under active sensors, and they are also exteroceptive. They measure something that is coming out, external to a mobile. And similar things can also be said for vision sensors. Actually, those are also exteroceptive passive sensors. Okay, so once you have decided on actuators, you also need to see whether the specifications of this actuators is right for your particular application. So in order for you to do that, there are several ways of characterizing the sensor's performance. There are some key terms that we should be aware of if you have to select the right specification of actuator, specification of sensors. So some of the key terms that we would be recalling now are what we call as dynamic range. So that is nothing but simply the ratio between upper limit and lower limits of the measurements, actually, usually expressed in decibels. So if you are inclined to measure sound, you can simply measure the sound in decibels using the ratio of the max sound it can measure to the max range or the upper limit by a lower limit. And mostly we would take the decibel of the maximum and minimum limit. So most of the cases we have a reference signal, actually a reference signal, uh, and we would take the measured ratio between the logarithmic ratio between a measured signal and a reference signal in order for us to have a quantify of how quantify how loud, or what is the relative uh, scale of measurement compared with this reference value. So yeah, that is what we use dynamic range for. And there is also one more term that you may come across. It's called range. So that is simply the uh, upper limit of measurement capability of a sensor. Then comes what we call as resolution. So resolution, in the sense, it's simply the minimum difference between the two values that can be detected by a sensor, actually. So like you would be mostly familiar with resolution of a display, the number of pixels per inch. So that is also a good measure of resolution. How many pixels are there? Like if there are more number of pixels, you will get more resolution. And for example, if you are interested to measure distances, if the minimum distance between two values are smaller, you will get a better resolution, right? If the minimum difference between two values are 1 millimeter, and if the minimum difference between two measurements are 1 micrometer, obviously the thing with 1 micrometer has more resolution, and it can be used to get even more accurate readings of uh, displacements or lengths, actually. And yeah, some other another aspect or another characteristic is what we call as linearity. It simply denotes the variation of uh, it simply denotes the variation of output signal. It's not input. Output signal as a function of input signal. So yeah, more often it may not be linear. So like it may be easy to get misleaded by this heading or its name, linearity. It has nothing to do with how linear the input is. How linearly the output is varying with respect to this input. It simply is a measure of how the output signal varies with the input signal. Like for example, until the input signal reaches a threshold, you may not even get any sort of output signal. So only when the input signal reaches a threshold, only then you will start receiving some sort of output signal. And it may not even vary linearly. It can be exponential, or it may be decreasing after a point of time. It may not be linear at all. So it's only to measure how, just to measure just to quantify the variation of output signal with input signal. So like I'll again give you one example. Like if you are using joysticks to play games, or if you are using some sort of a steering wheel to simulate the motion of a car, maybe in racing simulators. Uh, Initially, if you when the steering is at its own dead center, if you tilt it very small, very lightly, there won't be any movement. It won't register any movement. But if you turn it very fast, you may get a very high level of input, actually. So you can basically tune it as per your application, how whether it should be moving, if you are actually tilting the steering at a very fast rate, how much it should be moving, whether it should be moving linearly or whether it should be proportional to the movement that you are moving, to the command that you are giving, or whether it is proportional to the rate at which it is changing. All these things comes under linearity of the sensors. And yeah, the next aspect is bandwidth or frequency. So this is even more familiar with us. It's nothing but the speed at which a sensor can provide a stream of readings. So like we often hear this bandwidth with the speed, associate bandwidth with the speed of our internet connection. It's also similar, like how much of how much speed it can receive, or a system can receive, uh, uh, or how much yeah, the speed, how much the rate at which a sensor can actually deliver data uh, to a system, actually. So that is more or less what is covered by bandwidth actually. So often a time it's more or less limited by the sensor's sampling rate. So if the sensor samples at a larger intervals of time, obviously it may the bandwidth or the frequency at which it collects data decreases actually. So like if we have a high frequency of data, like if the application has high frequency of application, and if the sensor has only low frequency, it may not even capture uh, you know uh, it may not even capture uh, the intermediate points. When the sensor is not sampling, it may not even capture the features that is basically happening during the sampling rate and all those things. Yeah. So yeah, then there are some characteristics that are relevant for the real world environment. So like earlier, it was more or less related to the specification of a sensor. Now, all these terms that we are looking at at the moment are more or less, uh, something that has to do with the effect or the influence of the environment on the sensors. So one such thing is called sensitivity. It's nothing but the ratio of output change to input change, and it can be actually influenced by environmental factors such as illumination. The other thing could be humidity and all those things. Like if you are measuring a temperature, if the humidity is high, it may record some other temperature. Or if the measuring bulb is actually fouled, if it is fouled with some impurities or dust, it may not even register the right correct level of sensors. So that could be one factor. There is also one more thing that is called cross sensitivity. So that is something but the sensitivity of a sensor to the environmental parameters that are orthogonal to the target parameters. So like for example, if you are measuring one thing and the thing that we are measuring is getting affected by some other external parameters that are orthogonal to the uh, coordinates or orthogonal to the parameters that we are actually measuring. Like for example, if I don't know, for example, if we simply take a look at maybe the orientation of a robot, uh, it could be it could be maybe if you are using magnetic sensors and all those things, it could be affected by if something magnetic is actually coming at the proximity of the sensors, the entire thing can go disoriented, right? If a sensor is actually measuring using magnetic principles, maybe if it is measuring using orthogonal, Hall effect sensors as a proximity sensor, and if the robot is at close proximity to something, some other magnetic field that is nowhere related to its application, it may get affected actually. Its sensitivity may get affected, and more often can lead to incorrect sensor reading. So those things, getting affected by parameters that are orthogonal to what we are actually measuring. So those things we call those things as cross sensitivity. And ideally, most of the cases, we would like to keep this cross sensitivity minimal. So we only need to measure what we are trying to measure. It should not get affected by anything external to the environment. And yeah, there is one more thing, what we call as accuracy or error of the sensor. So like it's a broad term, it does not really apply to sensors as such as been expressed by this equation. It's nothing but a difference between this measured value and the true value, which should be measuring by true value. So this is nothing but this error actually, difference between measured value and true value divided by measured value. This is nothing but the error, fraction of error. And if you subtract it from 1, you will get the accuracy of the robot. Or you can simply do like instead of doing 1 minus m minus v by v, it'll be nothing but m by v. You'll also get the same expression if you simply do it m by v also. Yeah. And yeah, there are also few other things that while selecting sensors or while deploying sensors, there are few more challenges that we would encounter. So those are mostly related to errors. Actually, the different kinds of errors the readings of a sensors would be subjected to. So one of such errors is called systematic errors. Systematic errors or deterministic errors. So we can exactly model and eliminate systematic errors from a system. So that is why it is called deterministic, because we can exactly model it. And also, like, once we have modeled it, or once we have fully understood these kinds of errors, we can also fully eliminate it. Maybe, for example, it could be caused by factors that could, in theory, at least in theory, it could be modeled, because it could be well established by physical phenomena, and as we all know, we can more or less model most of the physical phenomena in theory. And proper calibration of sensors will most often eliminate these sort of systematic errors, right? So, like, for example, if you are using some sort of an optical sensor, and the errors in calibration, errors in measurements can be eliminated by proper calibration of the corresponding devices. And there are some other class of errors called random errors, which is also called non-deterministic errors. So this is more or less a gray area. Like, we cannot exactly pinpoint on a reason or a specific reason why these errors are happening. Maybe it could be, if you are trying to model a robot, theoretically you can model everything with zero joint clearances. If you model everything in CAD, and if you try to simulate uh, motion of a robot in a uh, CAD environment or a virtual environment, it will move exactly how you predict. But when you build it on real time, there could be errors due to manufacturing tolerances. Maybe not all the wheels are of the same size. Some could be slightly larger, and due to that fact, it can have some sort of errors, cumulative errors, due to the fact that not all the wheels are of different dimensions. And there could be errors due to joint clearances. We cannot exactly model, or we cannot exactly capture all these factors into this model, right? And one another such example is the hue instability of the camera, black level noise of camera. So, like, we cannot, however hard we try, we cannot really eliminate any sort of noise from any sort of sensors. And yeah, and due to that fact, since we don't know the source of these errors, and due to the fact that we cannot model these errors accurately, we cannot predict, or we cannot fully eliminate these sort of errors that we call as random errors. But however, we can model it probabilistically, and that too subject to some assumptions. So you will see that how these sort of errors can be modeled, and how it propagates through the model. Propagation in the sense, how the errors in sensors propagates to the measurements, or to the exact location of x, y, theta location of a robot. So the error propagation and all those things, we will see that in detail in the next week 5 lectures. And another key aspect is, the precision of the sensors. Like, for example, precision is basically the reproducibility of sensor errors. So precision basically means, how well or how accurately can you reproduce a measurement reading. So, like, for example, if you for the first measurement, you will get the reading as maybe this coordinate, and maybe for the second measurement, you still get this as the coordinate that you're interested. And for all the time you are getting the readings that are very close to this coordinate, you can call this as a high precise reading. But if the measurements are all over the place, then automatically that becomes a reading that is of less precision. So precision is repeatability. It's another word for repeatability. How much you can reproduce this errors, or how much you can reproduce measurements for during multiple tries. Yes. Yeah. So again, that is one aspect. Yeah. So most we will restrict ourselves with uh, what we have covered so far until now, because this week has been mostly regarding sensors, because I think for three or more lectures, the we have discussed about different kinds of sensors. So three lectures have been dedicated for the working principles of all sort of set of huge comprehensive set of sensors, which I do not wish to discuss here, because those are all theoretical and quite really well elaborated during this lectures, right? And yeah, and due to the fact that the lectures are all mostly theoretical, descriptive, you can also expect similar sort of questions, because until now we have solved some numerical problems regarding the kinematics of robots. But here this is more descriptive, but it can get more computational for the next week, because there we would be seeing, odometry, how to predict, how to propagate the errors from sensors to from the sensors to the actual location of a robot. All these things we will go through on the next week. So, like with that, I wish to conclude the summary of the topics that we have discussed for this week through the lectures for this week. And yeah, maybe we can solve some sample problems regarding the topics that we have discussed for week 4. So it's mostly, as you can recall, it's mostly about the working of the sensors. So yeah, that's about it. So yeah, one question is, which of the below system is constrained to perform tasks have the least complexity, given the systems have the least sensing and perception capabilities, right? So earlier we have seen a flow chart which maps, yeah, I think I will reproduce that image actually. So if you can recall from the beginning of this session, we actually have seen a graph that correlates the complexity of a task with the level of automation that can be incorporated onto the robot. So as you can see, like if the complexity of the task increases, uh, the level of human intervention becomes more and more necessary, becomes a necessity actually, because I feel like our current state of sensors and actuators are not matured enough to do complicated, tasks of very high complexity. For example, similar to how a human being, for example, to replicate all the functional features of a human being. So, like as the task complexity increases, the level of human intervention becomes a necessity. So, in that case, the robots operate, robots deployed on applications requiring high task complexity will be mostly remotely operated, right? Remotely operated. And if the complexity of the task is more or less if it can be easily handleable, or if it can be dealt with the existing sensors and actuators, we can incorporate some level of automation onto a robotic system, which makes it autonomous actually. And due to the fact that it could be much more cheaper on the longer run, right? Because these days labor costs are actually increasing on the high. And on a long term, if you are employing some sort of an autonomous system, if it can replace labor, it can actually replace labor costs. And on the long term, what you invest on autonomous systems would be much cheaper than the labor costs that you would be uh, investing. But due to the fact that our sensors and actuators are not really matured, or our power of computation still have not matured, the level of task complexity for higher level of autonomy is still very low. So yeah, with that insight, how can we answer this question? If you go back to the question, which of the system below is constrained to perform tasks having least complexity, given the robotic system have least sensing and perception capabilities? So yeah, is it remotely operated mobile robot, teleoperated surgical robot, an autonomous underwater robot, or hybrid robots? So yeah, so what does remotely operated mobile robot means? Remotely operated means it does not have it has very limited level of uh, sensors actually available to its sensor system, but it will still have some sort of yes, it will still have some sort of sensors, maybe and wheel encoders and all those things to exactly locate its position. And teleoperated surgical robot, so these are actually operated by a surgeon remotely. So it will basically have a slave controller, as it will basically be similar to a slave master slave configuration, where the surgeon would be working on a master system which would be remotely communicating with the slave system. So that would be what is operating on a patient. But the task complexity is actually high. It's very high because as you know, so robotic surgery is actually a surgical robot does very intricate tasks. You know how intricate this stitching, suturing, and all those things are. So it does tasks that is of huge. It's very highly complicated. And then what about the autonomous underwater robots? So the name itself says it is autonomous, and due to the fact that it is autonomous, it will have to have some sort of sensing and perception capabilities, because it will be deployed on an unconstrained environment. So it will have some level of sensing and perception capabilities. And hybrid robots, as you can see, comes somewhere in between remote and autonomous robots. So I suppose the question is clear, because yeah, I think the question is also somewhat confusing. It says if the system is constrained to perform tasks having least complexity, given the robot system has least sensing and perception capabilities. Okay, so I think the correct answer should be remotely operated mobile robot, because uh, that is something that has least sensing and perception capabilities, because it is fully remotely operated by an external operator. Because and since it is fully operated, it does not really need any sensing and perception capabilities. But teleoperated robot may probably require some sort of sensing and perception, because maybe as a fail-safe, or maybe if in order for it to prevent itself from catastrophically failing due to some other failure, maybe it may have some sensing and perception capabilities. So we'll take a look at this answer. It's okay. It's indeed option C. It says autonomous underwater robot. But yeah, I think,
This
yeah. What do you
this
think?
question is this question is
Confused.
quite confusing. One way we are saying
Yeah,
least complexity, and another
yeah,
way
yeah,
we are saying
yeah,
least.
yeah. Yeah, this question is probably quite confusing. So maybe if you get these sort of questions, if you probably raise it, maybe these sort of questions will be probably eliminated from the grading processes, because I think the question itself does not make much sense.
Your graph shows
Yeah,
least complexity means autonomous. Your graph shows least complexity means autonomous. Least
yeah,
sensing means remotely operated.
yeah, exactly. But I hope the graph at least makes sense, right? I hope the
Right.
graph
Yeah.
actually makes sense, because because something that involves, like, if you want to know about remote operation, you might have come across the surgical robots. So surgical robots are almost mostly operated by the surgeon himself, because
Okay.
we are still not in the right place to fully deploy a robot to do its own do a surgery on its own, because it could be very dangerous. So it's still controlled, or it's still fully remotely controlled by a surgeon. But the task that a surgical robot does is actually highly complicated. very intricate. Some of these tasks can only be made possible through surgical robots, because our hands can only make uh, I think if you bring the concept of resolution, the surgical robots can actually have even more resolution compared to us, to how a human can actually have. Because the motion of a human hand can be, using the surgical robots, it can be translated to micro level motions. So if some sort of suturing or some sort of stitching, or some sort of intricate suturing is to be done on a micron scale, you cannot do it by hand. You can only get the feedback from the computer screen using some sort of cameras, but you cannot use your own hands to do something that is on a micro scale. But with a robotic manipulator, you can basically translate your motion of your hands. You can basically transform it into the motion of that manipulator action. So I hope with that, I think that concept is clear, because as the task complexity is more and more complicated, you will have to the human intervention becomes more and more a necessity. But maybe in the future, maybe fully autonomous systems can also do highly complicated
Yeah,
tasks.
it's
But as of now,
clear now.
okay,
With
this
your
is how we
explanation,
should do.
earlier having trouble in understanding this graph.
Yeah, even I also found understanding this question. Maybe I shouldn't have added this question to this session, but somehow, I don't know, it does not make any sense right now. Okay. Okay, so moving on to question 2, it says the process by which people translate sensory impressions into coherent and unified view of world around them. So choose the process for which the above statement suits the best. So like for a mobile robot, like in the earlier slides, we have discussed the subsystems of a mobile robot, or rather an autonomous mobile robot. So these are the subsystems that comes under autonomous mobile robot. And which of them is which of these options is a better suit for the statement that we have just said, right? And so I suppose without much of a disagreement, we can all agree that this statement suits, perception is actually a better fit for this statement, because perception is all about creating a model of the environment around us. Like if you're talking about a human being, using our sensory organs, eyes, ears, and nose, we perceive the environment around us. We get a coherent, unified view of the environment around us. So that is what this perception is all about. And all the contents regarding this week 4 is all about perception. And for this upcoming weeks 4 and 5, we will progress from perception, from what we have collected from the sensors. We will utilize it for localization, to establish where the robot is on a given map. And cognition, like cognition in the sense, like once it has localized, or once it has a full grasp of its current position, then it needs to know where to go. And it should also have a clear sense of how to reach that goal position. So that is where this cognition step comes in. And later, once it has identified its goal position on a map that the robot is being supplied onto, later it proceeds on to the subsystem motion control, which makes sure that the robot stays on the most appropriate path. And it will also give the commands to the actuators. So motion control basically gives the actuators the commands while ensuring that the robot stays on the desired path that is selected, or that is chosen during this cognition. So this is where path planning and all those things comes. And motion control makes sure that the robot stays on the path that has been planned, and it will also give the necessary commands to the actuators. So with that, I think without much confusion, we can all agree that perception is the right fit for yes, the statement actually. Yeah. So I would also like to give us a brief screenshot of the various subsystem of the robot we have seen in the previous slide. So if this is the real world environment, this is basically a never-ending loop, an infinite loop that goes on forever as long as the robot is in motion. So if you begin your cycle from here, so using the sensors, the robot will perceive what are the features that it can perceive from this environment. And using all the features with the help of a local map, most of the cases we'll provide a map to the robot, and maybe we'll provide a map of the environment to the robot at the beginning, and we'll also give some goal position where on the map the robot would be moving. And once the map is available, the robot should localize its own position on the map. Like, for example, if the robot knows that these are the maps and there are certain landmarks on the map, so based on the sensors, it can basically determine its position from each of these landmarks. And based on that, it can localize its position on the map. So once it does that, then it will have to plan a path how to reach its from its start position, wherever it is on the map, to its target goal position. So that is done through this cognition stage where it plans a path from its current position to the goal position. And using the path it has been planned, once it is fed onto the motion control, the motion control basically gives the command to the actuators. And it also makes sure the motion control also makes sure that the robot stays on the path that has been planned during the cognition state. Okay, yes, so the answer is indeed option D. And yeah, moving on to question 3. Yeah, I think we have some internet bandwidth issues. Okay, so it says select the sensor system which cannot be classified as both exteroceptive and active sensors. So out of all the sensors given in this option, it cannot be exteroceptive and it cannot be an active sensor also. So what we are looking for sensors that are proprioceptive, and passive. So the options that satisfies that comes under a proprioceptive passive sensor should be the correct answer. So the first options are contact switches. So these are exteroceptive. It measures the proximity of an object based on contact. And since it is not powered it's only powered by physical interaction. So in that regard, it becomes a passive sensor. This is exteroceptive, and this is also a passive sensor. And what about non-contact proximity sensors? So proximity sensors in general are all exteroceptive. And since it is non-contact, it will have to emit some sort of an energy. And based on the reaction of the energy that it has emitted, it can use the reaction of its emitted energy as a measure of the parameter that it is trying to measure. For example, these ultrasonic sensors and all those things, it will first have to emit a sound wave, and based on the time for the sound wave to travel from its transmitter to be reflected back onto the receiver, it can have a measure of the distance between the robot itself or the sensor itself and the obstacle or this external body that it is whose distance it is trying to measure. So again, in that regard, non-contact proximity sensors are also exteroceptive, and they are active in that regard. And what about optical? So this is not optical, these are optical barriers. So optical barriers are also exteroceptive. It's also some sort of a proximity sensor or a position sensor, exteroceptive, and it is also it's also basically an passive sensor. And there could also be variants that could be active also. We can consult A comprehensive set of all the different kinds of sensors are all provided during one of the lectures actually. Where different class of sensors. We have tactile sensors. We have wheel motor sensors. We have heading sensors. All these sort of sensors and their classification, whether they are exteroceptive, whether they are active or passive. Uh, Hold on one second. I'm not sure whether you are seeing the right slide. Yeah, so as we were speaking, I hope I'm audible now. We were actually
Yes,
discussing about, yeah, sorry about that
sir.
connection issue. Okay. Yeah, so as we were discussing earlier, a comprehensive set of all sort of sensors have been discussed during the lectures. So, for example, we have discussed multiple varieties of tactile sensors and their classification, whether they are exteroceptive sensors or whether they are active or passive sensors. And exactly the same for wheel motor sensors. Like we have these much different kinds of wheel sensors. And again, same in the case of heading sensors over here. And what else do we have? We have ground-based beacons actually. So if you can take a look at this, I think this optical barriers, it may come somewhere here in the case of ground-based beacons and all those things. Uh,
Sir,
Or yeah,
no,
these comes under tactile sensors actually. Yeah. So this is
sir,
also
one
of
question.
yeah,
Sir, I missed something over here. I
uh,
understood it as having contact or not having contact. But
yeah,
here we are showing the four types of sensors, sir. Extra sen PC, EC,
yeah,
ARP.
yes.
Can you tell the difference between these four types?
Okay. So I'll go back to one of the previous slides actually. So it comes under the classification of sensors actually. You can classify sensors based on two different kinds of classification. So one kind of classification is called proprioceptive or exteroceptive sensors. So what does this mean is that the proprioceptive sensors are sensors that measure something that is internal to a robotic system. For
Oh,
example,
okay.
things like battery level indicator or maybe, encoder reading from the motors, how much the angular velocity of the motors, then its position and inclination. All these things are internal to a robot. So that those comes under proprioceptive sensors. And when the sensors that are measuring something that is external to a robot, for example, proximity to a wall or proximity to an obstacle, or maybe if you are talking about a camera, a vision sensor that is also measuring something external to a robot. So those things comes under exteroceptive sensors, something that is measured external to a robotic system. So that is one type of classification of sensors, proprioceptive and exteroceptive. And there is also second classification for sensors. It's called active and passive sensors, active or passive sensors. And passive sensors are something that it does not really, we don't have to supply any energy onto a passive sensor. It will get its own energy to function from this environment.
Okay, sir. I
Yeah.
understood.
Yeah. And active sensors, the exact opposite. For example, ultrasonic sensors, if you have to, you have to emit some sort of a sound wave to measure the position. So a sensor can be either, it can come under either proprioceptive or exteroceptive. It can fall on this classification and it can also fall on this classification, right? For example, if you talk about this ultrasonic sensor, so it basically measures a proximity to an external object. So due to that, it is an exteroceptive sensor. And due to the fact that we have to provide some sort of energy for the functioning of an ultrasonic device, it also is an active sensor, right? So based on this two classification, an ultrasonic sensor is an exteroceptive sensor. It is also an active sensor. So that is also what we are looking from the question. So it says which of them is not, yeah, it's written in a confusing way. It says which cannot be classified as both exteroceptive and an active. So what we are exactly looking for is proprioceptive and passive. So yeah, this optical barrier that is also used as tactile sensors. So since it is tactile, most of the tactile sensors are exteroceptive because it is actually measuring something that is external to a robotic system. So optical barriers are exteroceptive, and if you can look at the slide that I have reproduced, yeah, optical barriers are also active sensors because as the name suggests, it's as an optical term in it, that means it has to emit some sort of a energy, light energy, for it to function. So that becomes an active sensor. And what about gyroscope? So gyroscope is also used to measure something that is internal to a robot, the orientation of a robot, how far it is oriented. And depending on the kind of gyroscope, whether it is, if you can recall the lectures, there you might have discussed a lot of different kinds of gyroscope, whether it is a mechanical gyroscope, whether it is uh, MEMS gyroscope, or whether it is an optical gyroscope. So depending on the kind of gyroscope, it can be either active or passive. But since it is only mentioned as a gyroscope, you can assume it to be a mechanical gyroscope. And mechanical gyroscope basically comes under this heading sensors actually. Heading sensors mostly deals with the measurement of orientation of the robot. And since I have already said that gyroscopes are measuring something that is internal to a robot, its orientation, that is a proprioceptive sensor. And due to the fact that we don't have to provide any sort of energy onto it, that is also a passive sensors. Passive sensor. So gyroscope is basically a proprioceptive sensor and it is also passive. And what about this one? Doppler radar. So Doppler radar, like earlier we have established, Doppler radar is something that works on the principle of Doppler effect. So you also know, like if you have a transmitter over here, transmitter, and you have a receiver over here, and transmitter receives something of a frequency f0, and the receiver receives, due to the relative velocity between the transmitter and receiver, the frequency of the energy that is emitted by the transmitter will be different to what it is being received. It could be a higher frequency or it could be a lower frequency than the transmitted frequency, depending on the relative position and depending on the relative position between transmitter and receiver. So again, this Doppler radar, since it is measuring something external to the robot, since it is measuring a velocity of something that is external to the robotic system. Maybe if you want to measure something that is moving, if you are staying still and if you want to measure something that is moving, velocity of something that is moving, you need to have a transmitter receiver pair. And obviously, since we are dealing with the transmitter, it has to emit some sort of an energy. So that makes it an active sensor. And due to the fact that it is measuring something external to a robot, if it is measuring the velocity of an external object, due to that fact, it also becomes an exteroceptive sensor, actually. So in that regard, Doppler radar is also an external exteroceptive and also is an active sensor. And what about optical encoder? So encoders are mostly used to measure the angular position or angular velocity of the wheels or mostly the motors actually. Like for the purposes of calculating the angular velocity of the robot or the displacement of the wheel. So in that regard, since it is measuring something internal to a robot, that is a proprioceptive sensor, but due to the fact that it is an optical sensor, it also have to emit a light wave or a laser beam in order for its functioning, because if you can recall the working of an optical encoder, it'll have a rotating disk over here with multiple slots, and it'll emit a laser beam from here, and at the other end it'll have a receiver. So based on the number of pulses the receiver receives, it can basically map that with the angular velocity or angular location of these encoders. So since it deals with the emission of a source of energy, that also makes it an active sensor. Right. So as per the question, we are looking for sensors that is proprioceptive and passive. And which of these options satisfy this criteria? So as far as I can see, I can only see this gyroscope that satisfies this criteria. That is not exteroceptive and active. So gyroscope is both passive and proprioceptive. So I think the only correct answer in this regard is a gyroscope. And yeah, it's very easy to make mistakes on these sort of questions, because as you can see, there are plenty of different kinds of sensors that are being, discussed on the lectures. And sometimes you may even get multiple right answers also. So like, unless you are very thorough with these tables, it could be a bit difficult, because I think for this question, it only has a single correct answer. But in this exam, it could come as a multiple correct answer question. Okay, so yeah, with that, I think that correct answer is indeed okay. Both cannot. So the options are actually A, D, and F. I think contact switches, uh, gyroscope, and optical encoders are all the correct answers. Does that make any sense? Both exteroceptive and active sensors. So contact switches are exteroceptive. And okay, so if you take a look at this figure, contact switches are exteroceptive and passive. But the question says uh, which cannot be classified as exteroceptive. I think the choice of answer is wrong, because as per what is being provided, I think the logical correct answer is indeed gyroscope. And I suppose these were the questions from the previous year's question, I think. Previous year's question paper had some sort of errors, I think. So, yeah, about that. So, what do you guys think? Do you
Maybe
think?
this question was given, maybe this question was given.
Yeah, yeah,
No,
yeah. But
maybe this question was given so that
uh,
we will not skip that. But otherwise,
okay.
remembering so many combinations, it's humanly
Hmm.
impossible.
Yeah, yeah. But this appears to be multiple correct choice questions. But
I'm okay with you.
I don't think
Okay.
options A and F are correct, because it says which cannot be classified as both exteroceptive and active sensors. So optical encoder is proprioceptive, but it is an active sensor, right? So that cannot be an option. And same for the
Right.
contact switches. Yeah, same for the contact switches. Uh, that is an exteroceptive. So this statement in itself is actually making, we can eliminate this. It's an exteroceptive, and it is a passive sensor also. So yeah, these are also not correct. I think the only correct answer is gyroscope. I think the key itself is actually wrong. Okay,
Agree.
so like, yeah, without any, I suppose, like, if we don't have any further conflicts, we can move on to the next question. Okay, so this is more or less a numerical question. So it's about gyroscope, and if gyroscopes, on the lectures of the gyroscopes, these sort of formulations are also being given. So it says, consider a robotic system having a mechanical gyroscope which reads the following spinning. Okay, which reads this following spinning and precision speed as 600 RPM and 40 RPM respectively. So for the given gyroscope, spinning with the mass of spinning disk radius, so mass and radius of gyration is given. Find out the reactive torque in Newton meters. So I suppose you know what this precisional motion is. So if you know how a top spins, so let me see if I can draw a top. So the top, once you deploy the top after spinning, it'll spin about its own axis, right? This is a top. This is the axis of a top. It can spin about its own axis, and it will also have an angular velocity about a vertical axis. It will basically precise. So while this is the axis of the top, as it is as the top is spinning, it will also have a precisional rotation about some other axis, right? And eventually this precisional radius will get increased, and eventually the top will fall down. So these two angular velocities are given. The angular velocity, maybe we can call it as omega. Omega is given as the spinning speed omega about its own axis is given as 600 rpm, and the precisional angular velocity. Precisional angular velocity in the sense the speed at which it precises about a vertical axis, that is given as 40 rpm, right? And mass is also given as 4 kilograms, and radius of gyration, you can call this as k, to be 30 millimeters. So the question is to find out this reactive torque in Newton meters. So like since we are only dealing with this precisional motion, there is actually a simple formula. I suppose it is discussed on the lecture. So this expression for this reactive torque, tau, is nothing but this this moment of inertia of the top, I, multiplied by omega, the spinning speed over here, and the precisional angular velocity, I omega omega p. So this is what gives the reactive torque on the gyroscope. So like you can basically use this reactive torque as a measure of the orientation of the gyroscope, actually, the level of precision. So that is one way. It's not really relevant to that sensor itself. This is more or less relevant to this gyroscopic torque, gyroscopic reactive coupled. So all the numerical data is simply provided, and this formula is actually very important. If you get this sort of question regarding gyroscopic reactive torque, you can actually use this expression to determine its reactive torque. So despite this, the moment of inertia is not directly given. So how do you calculate the moment of inertia? Like you are given the mass and the radius of gyration of the top. So moment of inertia is nothing but mass times the radiation of gyration square, mk square. Then you have this omega 600. Then you also have the precisional angular velocity, omega times omega p. But if you simply substitute this, you won't get the right answer. Everything will have to be converted to Newton meters. So everything will have to be converted into SI units. So yeah, how do you do that? The correct numerical substitution would be mass, that is 4 kilograms, times k square, that is 30. If you convert everything into meters, you have to multiply it by 1000, mk square. So this is moment of inertia. Then you have this omega, precisional speed, but that is given in RPM, radians per revolutions per minute. But you have to convert that into radians per second. So that is nothing but 2 pi multiplied by omega by 60. So RPM to radians per second is 2 pi multiplied by the the speed of rotation multiplied by 60. So I think I may have made it even more confusing. So whatever is given onto the question is not exactly angular velocity, it is RPM. The spinning speed and precisional speed are given as RPMs, not as angular velocities. So you have to convert it into angular velocities using this 2 pi n by 60. And you also have one more 2 pi NP, the precessional speed. This is NS, this is NP. Yeah, NP by 60. So once you substitute that, you will get the right answer. And I don't think any options are given. So this is a numerical choice. So you have to, yeah, you have to enter that choice as a fill in the blanks question. So you are also asked to evaluate this answer up to 2 decimal places. So the correct rounding off the answer to the to 2 decimal places is also necessary. So if you don't do that, probably the answer may be marked as incorrect. Yeah, so once you do that, the correct numerical answer would be 0.94 Newton meters. Just I have discussed this reactive torque is nothing but I omega p. And since omega and this capital omega is still not given, you have to convert everything into uh, radians per second or angular velocity. But in the question, it is given as RPM, revolutions, rotations per. So that have to be converted to uh, angular velocities. Okay, so moving on, another question about sensors. So which of the following sensors are not incorporated?
Sir,
Yeah,
excuse me,
yes,
sir.
yes,
Excuse me, sir.
I can
One
hear you.
comment I
Yes,
want.
yeah,
Since in our last lecture, you said we should.
last
In our
lecture.
last lecture, in our last meeting, you said we should not refer to anything outside. Yeah, we have not. You said that we should not refer to any outside NPTEL sources, but I want to give a reference to an
Okay.
NPTEL resource where
Ah,
in Professor K. Ramesh of faculty from IIT Madras,
mhm,
NPTEL course, Engineering Mechanics, towards
uh-huh,
the last lectures,
yes.
35, 36, 37, he
Uh-huh,
talked about engineering precision uh,
uh-huh.
and he has shown the beautiful animations there. So maybe
Ah, okay,
if
okay.
students want,
That is
doesn't
very good.
understand, they can
Okay.
review that.
Yeah, because I think this precisional motion is actually a
Engineering mechanics
small.
course,
Yes,
engineering
exactly.
mechanics,
It's
yeah,
engineering mechanics, actually. Yes, it is basically a small subset of something that is even more complicated. So we basically derive this I omega p
it's an
reactive torque.
NPTEL course. And he
Yeah,
has shown beautiful animations regarding
yeah,
this.
yeah, yeah. Exactly, exactly. Yeah. So thank you for that. That could be very useful because it may be very difficult to digest how this expression has been derived because this is basically a simplification of something that is even more large. This has something to
Yeah,
do with
okay,
the three-dimensional rigid body uh, kinetics actually, and this precisional motion. This expression is merely a simplified case of this precisional motion actually, but in reality, it could be much more complex. And it all comes from this engineering mechanics. It all comes from the principles of engineering mechanics. So yeah, but the thing is that like I didn't suggest you shouldn't not review anything external. Like for the purposes of this course, you only need to uh, review what is being shared in this lectures. But if you are willing to learn, you can refer to any material. That is always encouraged, recommended. But
okay, okay,
yeah, but not everyone have time to do that actually. So that is why I recommend only to this thing. But if you are interested, if you want to know more about, how these specific relations are derived, the best way is to refer engineering mechanics, rigid body mechanics, mostly any material regarding any standard material regarding engineering mechanics, maybe a good textbook or as you suggested, maybe an NPTEL lecture. So yeah, that could also be very useful actually, because that is where most of the concepts that we derive here, they are all founded based on engineering mechanics actually. Whatever is being taught here, everything is more or less, derived from engineering mechanics. So that is the most fundamental, that is where the foundations of this course is basically laid on. Okay,
okay, sir. Thank you, sir.
thank you. Thank you for that suggestion. Okay, so moving on for question 5, it says, which of the following sensors are not incorporated on inertial measurement unit, estimating the 6 DOF pose of orientation system? So if you can recall what is being taught or what is being discussed on inertial measurement unit. So these systems are ideal for measuring 6 degrees of freedom, position and orientation sensors. So the positions can be measured using accelerometers in 3 directions actually. So like if you integrate the accelerations, you can get velocities, and if you further integrate, you will get positions. And orientation, you can basically get it from gyroscope. Gyroscope placed along 3 of these axes, right? So basically, inertial measurement unit essentially consists of gyroscopes in 3 axes and accelerometers in 3 axes, while the rest of them are not really part of IMUs, inertial measurement units, right? So which of them are not incorporated on IMU? So in that regard, the correct answers in this case would be optical encoders and vision sensors, because accelerometers gives you the linear accelerations, the linear coordinates, and gyroscopes give you the angular coordinates, angular accelerations or angular measurements of orientations. Yeah, so that is also pretty much options A and C, which are not part of IMU, optical encoders and vision sensors. And yeah, moving on to this is also another sensor-based problem. This is something what we call, the minimum number of satellites required for global positioning system to work, or GPS. So you know what a GPS is used for. GPSs are mostly used to exactly pinpoint a location of a receiver on the Earth. So, so some number of satellites will transmit some signal to a receiver on Earth, and based on the time it takes for the receiver to get its signal, it basically narrows down the position of that receiver to a very high accurate value. So in order for the system to work, what is the minimum number of satellites? Is it 2, is it 3, or is it 24, or is it 4? So yeah, I'll basically give a small overview of this GPS system. It's also taken from the lectures from professor. So like GPS is a system, global positioning system developed by USA for, it's mostly intended for military use. Later, it has been adopted for civilian use, and it consists of 24 satellites. Like even though you may not require 24 satellites to pinpoint a location of a receiver, because to improve the accuracy, it has redundancy built onto them. So it consists of 24 satellites, and it also has 3 spares. So if one of the satellites goes out of operation, the spares can come and take its position. And it orbits Earth every 12 hours at a height of 20.19 kilometers. And yeah, there are 4 satellites that are located in each of the 6 planes inclined at 55 degrees with respect to Earth's equator. And the location of GPS receiver is determined through time of flight measurement. The time is for a signal to reach from the transmitter from a satellite to the receiver at the user end. Okay, and there are some technical difficulties. There could be some time synchronization between individuals and satellites between receivers, because it takes a lot of time for a signal to reach from uh, the transmitter and receiver, and the time elapsed may not be time between the different satellites have to be synchronized in order for us to get a real, to get a more accurate measure of location. And the real-time update of exact location of the satellite. So the location of the satellites themselves are also crucial, and the precise measurements of time of flight. Sometimes, due to the curvature of the Earth, it may not be as straightforward as you would imagine. And there could also be interferences with other signals. So the reception, maybe at the very remote location, GPS signals may not be easily receivable. And the principle is elaborated on this slide. So if you consider three satellites, one over here, one satellite here, another satellite here, and another satellite here. So this is satellite one, this is satellite two, and this is satellite three. And if you consider each of the satellites to transmit some signal, and the receiver on Earth captures these three signals transmitted by these three satellites, and based on the time it takes for the receiver to receive, it can basically determine the distance, the location of this satellite. Right? It's nothing but the speed of sound multiplied by the time taken. Right? So if that is known, this as far as this satellite is concerned, the position can be anywhere within this sphere. Right? From the estimate of velocity of sound and velocity of the time taken. If you draw a sphere of a constant radius, the position according to this satellite can be anywhere that within the sphere. And if we consider satellite 2, based on its time of flight and speed of sound, the position can anywhere within this sphere. Then what will be the correct location? So if you intersect these two spheres, you will get a circle, right? So basically, intersection between two spheres is a circle, right? So a circle is also not a final estimate. So from a third satellite will also, based on its time of flight and speed of sound, it will also have its, again, another sphere of influence. And from the circle, an intersection between a circle and a sphere are 2 points. It's simple geometry. So intersection of spheres between satellite 1 and satellite 2 is a circle. And the intersection of this circle with the sphere of the third satellite is 2 points actually. One could be on Earth, one could be somewhere else, not on Earth. And from a signal using a fourth satellite, just to synchronize the time, then you can eliminate one of the point. You can actually eliminate one of the point that is not on Earth using the data from a fourth satellite. And you can basically exactly know which is the correct point. Out of these 2 points, you can exactly pinpoint from the data from the fourth satellite, you can exactly pinpoint the correct point of intersection. So 3 satellites will not be enough because 3 satellites will give you 2 positions, 2 possible positions, and you require one more satellite to finally pinpoint the final location. So that makes it 4 satellites in order for us to exactly determine its pinpoint. So yeah, with that, I suppose we can answer the question. The minimum number of satellites required in a GPS system is 4. Because 2 satellites will give you a circle of possible points. 3 satellites give you 2 points, and the 4 satellites will enable you to narrow down to the single point. That is the correct point. Okay, so yeah, moving on to question 7. It is also somewhat related to this time of flight application, but it's a simple problem. A floor cleaning robot is placed at a position A, and it detects an obstacle at position B with the help of an ultrasonic sensor. So the sensor values are as follows. The speed of wave propagation is 340 meters per second, and time of flight is 0.04 seconds. So find the distance between A and B in meters. So you have a robot placed at position A, and there is an obstacle at position B, right? And the speed of sound C is 340 meters per second, and the time of flight is maybe T as 0.04 seconds. So then what is the distance between A and B? So you are given the velocity, you are also given the time. So the distance is nothing but velocity multiplied by time. So C, speed of sound multiplied by time. Would this be enough? There should also be a 2 under 2. You should divide this by 2. Yeah, because the transmitter and receiver are both on the robot. So the signal will have to go forward, and it will also have to come backward. So that is what this time of flight time of flight mean. So 340 meters per second multiplied by 0.04 seconds, all divided by 2. This will give you the correct answer, which is the distance between these two uh, points. So I think the correct answer in that regard, if you do this, c times t by 2, this is 6.8, around 6.8 meters per second, right? I think this is a fairly straightforward problem. There would be ambiguities to in rounding off these errors. So yeah, as per the answer key, any answer between 6.9 and 6.8 is acceptable. Okay, so similarly, moving on to question 8. So dash is a method that is used for controlling a robotic device remotely by a human operator. So if you can recall the slide that we have shown at the beginning, there were two different kinds of, or two different modes of operation, that is teleoperation. Teleoperation, and there's another mode at the other end. You have this autonomous mode of operation. So dash is a method used for controlling a robotic device remotely by a human operator. Is it telepresence? Is it autonomous operation mode? Is it navigation? It is teleoperation. So I don't think we need to further elaborate further on this. This is nothing but teleoperation. Mostly how rovers on other planets or moons are operated by uh, a base on Earth. Or if you simply control a robot by a joystick, if you simply build a mobile robot without any level of autonomy, if you simply control all the motors using the inputs from a joystick, that can also be considered as a teleoperation. So that's nothing but controlling a robotic device remotely by a human operator. Yeah, so that is also a fairly simple question. Okay, so another question is choose the correct statement. Okay, so proprioceptive sensors gather information from the robot's environment. So that is by definition false, because proprioceptive sensors gathers information which are internal to the robot, and exteroceptive sensors measures value internally to the system. So that is also false. So the correct statement would be these two inverted, proprioceptive. So this statement applies to exteroceptive. This applies to proprioceptive. And the third statement, passive sensors acquire energy from the environment for their functioning. So again, by definition, that is true. And active sensors emit proper energy and measure their reaction. That is also correct. So in this regard, both of these options are true. This is a multiple correct answer question. So yeah, both of these options are indeed true, yes. And we may have few more questions, maybe 4 or 5 questions. So yeah, this is a match the following kind of a question. So yeah, this is a general classification, and you have to choose the correct option from what is being given on table 2. So yeah, tactile sensors, it could mean anything. There could be multiple tactile sensors. So out of this, which is a tactile sensor? Yeah,
Sir,
sorry
your
about
voice is not audible. It's muted.
Okay, okay. I suppose it's audible now.
Okay.
Yeah, maybe for some reason it's getting terminated. Maybe if next week onwards, maybe I'll try to see if that is not happening. Yeah, it's a simple problem of match the following. I suppose I'm audible now. Okay. So which of this is a tactile sensor? Is it brush encoders? Encoders is not a tactile sensor. It is mostly used for odometry. You will see odometry on week 5 to measure a robot's position, and yeah, mostly used for positions. Is it GPS? No, that is not correct. Contact switches is a good choice, right? We have seen this earlier. This is a exteroceptive passive sensor. So yeah, tactile sensor is contact switches is a tactile sensor. Yeah, so one corresponds to D. And what about wheel motor sensors? So in order for us to get an estimate or to get this correct angular position of wheels or motors, which of them is the correct right sensor in order for us to do that? It's the brush sensors actually, wheel motor sensors. An example for a wheel motor sensor are this brush encoders. So option 2 is A. And for 3, heading sensors. Heading sensors are mostly for uh, getting orientations, actually, to measure orientations. So which of these are suitable for measuring orientation? It is this inclinometers, actually. As it measures, it basically measures inclinometers. So to be more specific, the pitching, depend on pitching of a robot. So you can also call this to be the correct answer. So option 3 corresponds to E. Then what are the remaining? Ground-based beacons. So GPS also based on ground-based beacons. 4 is option B. Because in GPS, the beacons are actually placed on the ground. So depending on how the signal is being received by the beacons on the ground, the receiver on the ground, you can basically determine the exact location of that beacon. Then what do we have? Motion-based sensors. So like earlier, what we have discussed, Doppler effects or the Doppler phenomena can be used to measure motion of objects, actually motion of obstacles. So 5 is obviously F, and vision-based sensors, that is option C, charge coupled devices. CCD cameras, that is vision sensors, 6E. Okay, so which I think option D is the correct option. Option 1D to, sorry, I think option B, I think, yes. Again, I think there is nothing much to be discussed about because these are all theoretical and also discussed very thoroughly, very elaborately during the lectures. Okay, so the answer is option indeed, option B. And question 11, what does it say? So which of the sensor performance characteristic fits the following definition? So like we have actually seen what does each of the specifications mean? What does dynamic range means? What is the meaning of range, resolution, linearity, bandwidth? We have all covered that uh, in this session, earlier this session. So the statement is something dash is the minimum difference between two values that can be detected by the sensors. Minimum difference between two values. So is it dynamic range? Is it range? Is it resolution? Is it bandwidth? Correct answer by definition is indeed resolution. Actually, resolution. Right? For example, like if you have a scale, most often the scale, a ruler will have minimal difference that you can have as 1 millimeters. But if you take a vernier caliper, it can have up to 0.02 millimeters as least count. So in that regard, you can actually say a vernier caliper has more resolution or it has more resolution. It can detect even smaller values that a ruler or a regular steel ruler can actually measure. So in that regard, the correct answer is indeed resolution, right? And moving on to question 12. This is also a simple numerical problem. So if the measured value is 35 units and the true value is 37 units. So what is the accuracy of the sensor? If the measured value is 35 and the true value is uh, 37, then what is the true accuracy of that sensor? So it's nothing but 35 by 37, right? Whatever you are getting, whatever you are getting, the measured value by true value, that is nothing but this accuracy of the sensor. Right? If you get 37, it will be 100% accuracy. If you get only half of it, it will be half of 37, 50% accuracy. If you are getting 35, then the accuracy would be simply nothing but 35 by 37. And I think the correct answer is 94.6, 9.946 actually. Yes. But maybe sometimes it may ask, what could be the error. So if it is the error, then you have to, subtract it. It should be 37 minus 35 by 37. If the error was asked, you should have done this. But since it is accuracy that has been asked, it's nothing but 35 by 37. In the lecture, you might have come across this formula 1 minus m minus v by v. And this term is simply error. And this term is, if you subtract one error from one, you will get accuracy. So that is also true. We simply did this on a single step since accuracy is asked. Okay, so the answer is indeed 0.946. And yeah, moving on to question 13. Again, you are asked to find out the wrong statements. So I think the first two options are mostly dealt with capacitive and inductive proximity sensors. So we'll come back to that later. What about this? Minimum number of satellites required in a global positioning system are 24. So that is indeed wrong, right? The number of systems in a GPS system is 24. That is correct. But minimum number of satellites required is not 24. It is 4 because you only need 4 satellites to exactly pinpoint the location of beacon on the ground. So that is a false statement. And what about contact switches and bumpers are passive switches, passive sensors? That is true. So that is actually quite true. Contact switches and passive sensors are true. Those are also proximity sensors, and they actually function on the physical interaction between the sensor itself and the environment. So you don't need to supply any energy onto them. So those are indeed passive sensors. But what about capacitive and inductive sensors? It says capacity proximity sensors can detect both metallic and non-metallic objects. Is it true or false? Inductive sensors are more accurate than capacitive sensors. So I'll simply give a brief recall about inductive sensors. So this is also a screenshot from the slide. So yeah, basically what inductive sensors is that inductive sensors, when it comes in close proximity with a metal object, uh, due to the influence of this metal object, it will basically create some eddy currents. It will create some eddy currents due to the interaction between the magnetic field of this inductive proximity sensor with the metal object. And this eddy current, this change of eddy current or this magnitude of this eddy current can be used as a measure to determine how close that metallic object is. So with that regard, it is very highly accurate compared to other technologies because it's only measuring this eddy currents actually, and if you calibrate the current measured with the proximity to this object, the whatever it is measured can be highly correlated with the proximity of this object. And it can also work in harsh working environment, no problems in that. But the only drawback is, they can only be used with metal objects. They can only be used to detect metallic objects. But an advantage is their higher accuracy. Actually, it says it can work in harsh environments, and hence it can have higher accuracies. It's highly accurate. So going back to this options, inductive sensors are basically, inductive sensors are actually highly accurate. So that statement is actually true. Inductive sensors are more accurate than capacitive sensors. And if you go to one more slide, this is also a screenshot about capacitive sensors. And capacitive sensors basically it detects the change in capacitance due to the presence of an external object. So if the capacitance between the two plates changes due to the change in the dielectric medium or due to the presence of an external body, there will be a change of a capacitance, and hence there will be a change of current passing through that through that capacitive sensors. And the advantage of this that it only needs the presence of a foreign body. It does not have to be metallic. So in that regard, it can detect non-metallic objects such as liquids and plastics. So yeah, those are its advantages. It can detect metallic objects, metallic as well as non-metallic objects. They are much more faster. They have higher sampling rates. They have good stability, good power usage, and they are also cheaper than inductive sensors. But the disadvantage is that they are not as accurate as inductive sensors. They are affected by temperature and humidity. They are not accurate as inductive sensors, and they may also have some sort of difficulties in designing. So in that regard, what would be the correct answer? So it says capacitive sensors are, capacitive proximity sensors can detect. That is a true statement, actually. This is true. It can detect metallic and non-metallic objects. So inductive sensors are more accurate also. That is also true. And we have already seen that this statement is actually false, because we only need 4 satellites to exactly pinpoint a location of a beacon on Earth. It's not 24. That is a wrong statement, actually. This is a false statement. And contact switches and passive bumpers contact switches and bumpers are also passive sensors. So that is also true. So the question asks to find out the wrong statement. So the only wrong statement here is this one about the GPS. Okay, so yeah, that makes it the wrong answer. Yeah, so we'll again go with the final question of this session. So this is a problem regarding this Doppler effect. So as you know, this Doppler effect can be used to estimate the velocity or relative velocity between a moving transmitter or a moving receiver. Both could be in motion, or one could be fixed, one could be in motion, whatever be the case. So it basically says the siren of a police car emits a frequency of 1200 hertz. So we'll denote F0 as the frequency of the emitter. So I'll write it here, emitter frequency as 1200 hertz. And the police car basically moves with a constant speed of 30 meters per second away from the stationary observer. So the velocity of this emitter, uh, emitter velocity, maybe how do you call that? Vs is 30 meters per second. And we also have some data about the receiver or observer. I'll call this as receiver data. So yeah, it says it moves 30 meters away from a stationary observer. So observer velocity is 0. It says the receiver is stationary. So the velocity of the observer is 0. So it says what is the frequency of the siren the stationary observer will observe. So F receiver, how much would be the receiver? What will be the frequency as observed by the receiver? And you are also considered to take the velocity of the sound. Maybe we denote it as C, as 340 meter per seconds. So like we might also have observed this phenomenon of Doppler effect. Like if you have seen this, for example, if an ambulance passes us, as it approaches us, its frequency keeps on increasing, and as soon as it passes us, you can actually see that the frequency of that siren is decreasing. So because the frequency that is emitted by the transmitter is not what we perceive. We may perceive it to be higher than that when the transmitter is approaching us, or we may perceive it as something that is lower than the transmitted frequency as it is moving away from it. So the basic concept is that the ratio of the emitter frequency and the receiver frequency is basically nothing but the ratio of the relative relative velocities, maybe the relative velocities of the emitter. So C plus or minus Vs, C plus or minus V observe. Yeah, V observer actually. So the velocity of the emitter is velocity of the emitter is proportional to the frequency of the uh, emitter is proportional to the relative velocity of the emitter, and the frequency of the receiver is proportional to the relative velocity of the observer. Where the C is nothing but the speed of light, Vs is the speed of emitter, Vo is the speed of observer, right? And depending on the C, depending on how, if, for example, there could be multiple scenarios. So if we have observer here, if we have the transmitter here, there could be multiple scenarios. Maybe for one scenario, observer may be, stationary, and the transmitter could be approaching the observer. Another scenario is observer is stationary, but the transmitter is moving away from the observer. That is another scenario. Or transmitter could be stationary, observer could be moving towards the transmitter. Transmitter could be stationary, observer could be moving away. Both of them are moving towards each other. Both of them are moving away from each other. All these different scenarios are possible. So in order for us to accommodate all these different scenarios, that is where you would have to choose whether it's a plus or is it a minus, depending on the scenario. So like one example, like this is an excerpt taken from Wikipedia. So this basically summarizes it very well. So this is this is the frequency of the receiver. This is the frequency of the transmitter. So F by FO is simply proportional to the relative velocity of the receiver and relative velocity of the transmitter. And where to use this plus and minus, it is basically defined here. So like VR is the speed of the receiver relative to the medium. So if the receiver is moving towards the source, we have to add it to C. VR has to be taken as positive. If the receiver is moving away from the source, VR has to be subtracted from C. And same in the case of Vs, but that is flipped. If the source is moving away from the receiver, we have to add it with C. And if it is moving towards the receiver, we have to subtract it from C. So there is also one more shortcut way of remembering this. So F by FO is C plus or minus VR by C plus or minus Vs. So if you can recall, if for both of these cases, one example, if the transmitter is moving towards us, consider that scenario, transmitter is moving towards us, uh, we actually perceive a higher frequency than the transmitted frequency, right? So F should be higher than FO. F should be greater than FO. If the transmitter is moving towards the receiver, or if the receiver is moving towards the transmitter, then whatever the receiver perceives should be higher than the transmitted frequency. So in that case, this entire term should be greater than 1. This entire term should be, we have to make sure that it could be as high as possible. So how do you do that? If you want to make this ratio as big as possible, this numerator we have to add, right? C plus VR have to be higher, has to be added, VR. C plus VR will have to be added, because that is when this term can be maximized. And this numerator will have to be minimized. It has to be C minus Vs. So C plus Vs, Vr by C minus Vs will give you the largest values, largest numerical value for this term under this bracket. So if either the object is moving towards us, sorry, either the transmitter is moving towards the receiver, or if the receiver is moving towards the transmitter, you have to maximize the numerical value under this inside this parenthesis. You can do that by maximizing the numerator and minimizing the denominator, like so, C plus Vr by C minus Vs. And if the transmitter is moving away from us, or if the receiver is moving away from the transmitter, you can see that the frequency, you can actually perceive that the frequency is actually decreasing. So as the frequency is decreasing, you have to make sure that the term under this parenthesis is minimized. So how to do that? You have to minimize the numerator C minus Vr, and you have to maximize the denominator C plus Vs. So if you do that, this entire term will be minimized. So what is the scenario that we have? In the scenario, it says, as per the question, what is the question actually? The police car is moving with a constant speed away from the stationary observer. So obviously the frequency will have to be lower than 1200. It has to be lower than 1200 Newton because it is moving away from the receiver or away from the observer. So which of this option is actually correct? If it is moving away from this observer, we have to take this option because this is what we give. This is what we will give the minimum value on this parameter parenthesis. So if you simply substitute that, FO is 1200, C is 340 meters per second, VR is the speed of the receiver or the observer. So that is 0 because the question, it says the receiver is stationary. And the speed, again, the numerator would be 340. Sorry, this is 340 minus 0. That does not make any difference. This should be the correct formula, actually. This should be the correct formula. And the numerator should be C plus Vs. So C plus 340 plus, what was Vs? 30 meters per second. So if you do that, you will get observed frequency. You will get the frequency, observed frequency that is less than 1200. That is lower than 1200. So once you do that, once you do this calculation, the correct answer would be, I think, 1102 should be the correct answer, right? Or else F is F0 multiplied by C plus Vs. And this is when our observer is stationary. And the transmitter is moving away. Okay, so yeah, that is the correct answer. You can also expect similar kind of questions for this tutorial because numerical questions, it will be very simple as you have, seen in this live session. I think the only level of complex numerical question is only this one. All the others are simply a matter of, distance times velocity kind of questions. And you can also expect a few, descriptive questions, regarding the classification of sensors, maybe some match the following kind of questions that we have seen in the match the following kind of questions that we have seen in the earlier slides. All right. Yeah. So with that, I'll stop this session unless you have any further doubts. Without that, I can stop this session.
Thanks a lot, sir. Have a
Okay,
nice
thank
day.
you. Okay, you too as well. Again, thanks for repeatedly joining. Okay, thank you for your attention also. So, okay, see you then. Bye. Sure. Thanks.